Good morning. We have already discussed about the applications of conductance measurement in the previous videos, but today we'll basically we're going to discuss about some important theories, laws, and some important effects which are often observed in electrochemistry. Okay, and the first and the most important theory is Arrhenius theory. Arrhenius theory of electrolytic dissociation. Dissociation. Okay, so this theory is actually very important, and this is the basis of electrochemistry. Okay, so you must have to understand this theory to understand the electrochemical processes, okay, and the electrochemistry actually. So this is a very simple theory, okay, and but this is very important. So you can understand this theory by taking an example. Okay, so let's suppose you are taking a beaker and you are taking some aqueous electrolytic solution inside that beaker. Okay, so according to this theory, actually this theory gives mainly 2 points. Okay, so this theory consists of 2 points. So the first point is that the electrolytes in that aqueous solution undergo spontaneous dissociations. That means, let's suppose this is an electrolyte. Okay, so this electrolyte will going to this will going to dissociate it into their positive and negative ions spontaneously. So this is the first point. Okay, so according to the first point, what is the first point? According to the first point, we can say that the electrolytes, that means the molecules of an electrolyte in aqueous solutions undergoes spontaneous dissociations into their positive and negative ions. Okay, and according to the second point, let's suppose they are going to dissociate it into their ions. Okay, is positive and a negative. Okay, so there will be a time. Okay, so first of all, it will going to they will going to dissociate it into is positive and a negative. Okay, so again, if the electrolyte is your weak electrolyte, then the dissociation rate is not so the dissociation rate is not so fast, or it is a slow rate. Okay, the rate of this dissociation is slow. So that means there will be some time. Okay, that means that this ion will get some time to recombine again with each other. Okay, so that means there will be a chance of backward reactions. That means these two ions will again going to combine with each other and can form again the unionized ions. So after some time, okay, a point will be there. At that point, the forward rate reaction is equal to the backward rate reactions. Okay, that means the equilibrium will going to be there. Understand? So after some time, there will be a dynamic equilibrium between the ions. These are the ions, no? Ions and the unionized molecules. Okay, so there will be an equilibrium, and this equilibrium is known as actually dynamic. This is actually dynamic. Okay, so dynamic equilibrium will be exist between this unionized molecule and the ions. So this is the basic. Actually, these two are the 2 points which form that Arrhenius theory. Okay, so Please remember these 2 points. Okay, so before discussing about the other laws or theories, we will have to clear some concept. So why we actually write some here, what is the electrolytic solution? So electrolytic solutions means when we add some electrolyte in some solvent, then that solution is known as electrolytic solution. And what is aqueous electrolytic solutions? If the solvent is water, then that electrolytic solution is known as aqueous electrolytic solutions. Okay, so this is done. So now again, one more important point is that when we write some excuse me, some reaction or some electrolytic reactions, that means when we write the electrolyte here and they will going to dissociate it into their ions in aqueous medium, then we always write here aqueous. Okay, so why we actually write aqueous? The main point or the main concept behind this is that actually that electrolyte will going to dissociate. Okay, no doubt they will going to dissociate it into their ions, but here because these are what they carry some charges, no? So the cation will going to carry positive charge and the anion will going to carry negative charges. Okay, so when they have some charge, that means in the solution there will be the solvent is what water in aqueous solution. Okay, so that means here we know that in case of water molecule they have some dipole moment. Okay, because of that electronegativity defined, so this is your del negative, del positive, and this is del positive. Okay, so there will be some interaction between this negative and positive ions, so there will be a solvated sphere will be there. That means this hydrogen positive ion will be covered spherically by many water molecules. Okay, and to actually to define this one, or to actually indicate this sphere or the solvated process is we use that aqueous. That means this is in aqueous form. Okay, actually this is in H2O form. Okay, H2O positive form. So similarly a negative will also going to be solvated by that, but here it is negative now. Here water molecule has molecules have that is positive, that means H del positive will be here also, so that this del is positive or is del positive will going to interact with this one and they will going to form a solvated ions. Okay, so that's why we are writing here aqueous form. Okay, that means they are in solvated form. So I hope you understand the Arrhenius theory. So what we understand from Arrhenius theory, it is mainly consists of 2 points. The first point says that the electrolytes will going to dissociate it into their ions spontaneously in aqueous solutions. Spontaneously. Okay, so please remember that points spontaneously. Okay, and the second point is that there will be a dynamic equilibrium between that ions and the what that unionized molecules. Okay, and that equilibrium is actually known as dynamic equilibrium. Hope you understand the first theory. So now we're going to discuss a new law, okay, which is Ostwald dilution law. And basically this law is also on the basis of this Arrhenius theory. So here see, the Ostwald law is what? Ostwald law is based on Arrhenius theory. That means he used the concept of Arrhenius theory and he applies some other concept, or he adds some other concept in the Arrhenius theory, or we can say that he inspired he inspired from the Arrhenius theory, and he by the inspiration he gave one new law, and that law is your Ostwald dilution law. That's why the Arrhenius law is theory is very important. Okay, because it is the basis of electrochemistry, so that's why you have to know this theory properly. Okay, So next we are going to discuss about the Ostwald dilutions law. Okay, so let us now discuss about the Ostwald dilution law. Okay, so here actually Ostwald, he used the concept of Arrhenius theory. Actually, according to the Arrhenius theory, we already able to know that the ions, let's suppose here this is your electrolyte, okay, AB, and according to Arrhenius theory, we know that there will be some dynamic equilibrium between the unionized unionized molecule and their ions. Okay, let's suppose this is the ions, okay, two ions. So there will be a dynamic equilibrium. And always one point, please remember one point, that uh, the Arrhenius theory, okay, please remember this point, the Arrhenius theory and Ostwald dilution law is only applicable to weak electrolytes. Why? Because electrolytes will going to dissociate it completely into their ions. So if you consider a strong electrolyte, so can you give me some example? HCl or sodium chloride or sodium hydroxide, they are strong, no? Strong electrolyte. So this is a strong acid, no? So they will going to give this one. Is it right? No, this is not correct. If you write this way, then this will be wrong, because we cannot write this equilibrium, that means the reversible reaction symbol here. Okay, so we have to always use only one direction. Okay, that means it will going to completely dissociate it into their ions, and this process is very fast process. Okay, so once we add HCl in water, that means aqueous medium, then they will going to form H positive and Cl negative, okay, in that aqueous medium. It is a very fast process, so that means they that H positive and Cl negative will not going to get any time, okay, to recombine to form HCl. So that means this is a fast process, so there will be no any reversible reaction. If no reversible reactions means no equilibrium. Okay, so only we use that equilibrium concept in weak electrolytes. Okay, so remember this point, weak electrolyte means weak acids and weak base. Okay, so coming to the your Ostwald dilutions law, he actually inspired from that theory, that means Arrhenius theory. He actually write, or he did an experiment. Okay, so he just, let's suppose this is your electrolyte. Okay, Av is the electrolyte, and according to the Arrhenius theory, we know that this will going to dissociate it into their ions spontaneously, and there will be some dynamic equilibrium between these ions and the unionized molecules. Okay, so what he did, he just actually quantified this process. Actually he tried to find out that uh, uh, equilibrium constants for that reactions. But here this reaction is that ionic reactions now, and previously we have the idea about chemical equilibrium. In chemical equilibrium, what we studied about the chemical reactions which are reversible. Okay, that means reversible chemical reactions. We study the chemical equilibrium in that reactions. Okay, so here, but some ions are involved, so this chapter is actually this is actually related to ionic equilibrium. Okay, so here let's suppose this is your reactions, and we can use chemical equilibrium, that means the equilibrium concept in this reaction. Okay, so suppose at initial time, so we can go below. Okay, so wait, yes, so here in the PDF you can also see, that means the slide. Okay, you can see it. Okay, so it in initial condition, so also I will going to you know attach the link of this PDF file in the description of this video. Then you can, if you want, then you can download this PDF from the description. Okay, so don't worry. Let's suppose the initial concentration, and suppose the unit of the initial concentration is moles per decameter. So sorry, this is decameter cube. Okay, because we just divide that this one, so no need of minus. So you can express this one like this, or you can write moles into decameter to the minus 3, same thing. Okay, so at initial condition concentration, that means at time t is equal to 0, that means when time there will be no any dissociation, no? So time t is equal to 0 means when we just add the electrolyte in the solution before adding the electrolyte in the solution. Okay, so time t is equal to 0. So at time t is equal to 0, let's suppose the concentration of the molecule is A, B. Okay, suppose. Okay, so here at initial time it will be your 0 and 0. Why 0? Because there will be no any formation of ions. Okay, at initial time. So let's suppose at equilibrium position, at equilibrium position, the equilibrium concentration will be also in moles per decameter cube. So you can also express it like this one. So at this equilibrium position, that means the forward rate and the backward rate is equal. Okay, so suppose the dissociation constant is alpha. So if the dissociation constant is alpha, then C alpha will be the concentration of A positive. So I think you have already idea about this alpha, that means the dissociation constant in the higher secondary first year. Okay, in the higher secondary first year books, chemistry book and NCERT book, you can go through that book. Okay, so if you don't know, then you can go through that book. So this is your C alpha, and then also here also C alpha, the concentration of the B. Okay, so how that means then what will be the concentration of a that means the unionized molecule? It will be your C minus C alpha. Okay, so or you can write that C into 1 minus alpha, and this is your C alpha, and this is your C alpha, or same thing. Okay, so we have now the value of the concentrations of the unionized ions and the ions. Okay, so now we have the concentrations of different that means the unionized ion and the ions. So here we know that K is equal to, so this is a equilibrium, no? This is the reversible reaction. So for the reversible reaction, we can write the equilibrium constant, and we know that the equilibrium constant is defined as the, here you have to write the, you have to write or the concentration of the products, that means the multiplication of the products, active masses of product actually, but here you can replace that active mass by concentration. Okay, so here you have to write the concentrations of the that means product. So it means here A positive ion, the concentration of A positive ion, and concentration of B negative ions. Okay, and here it will be the concentration of your unionized molecule. Okay, so it will be, so here from this discussion we have able to know that at equilibrium conditions the equilibrium concentration will be C alpha for A positive and C alpha for B negative. Okay, so what we can write here, C alpha into C alpha, and in this case it will be C into 1 minus alpha. Okay, so this will be your alpha square C square C 1 minus alpha. Okay, so K equilibrium, so here also you can write equilibrium, okay, because it is equilibrium constant. So it will be your C alpha square 1 minus alpha. So this is actually your Ostwald dilution law. Okay, actually this is known as Ostwald dilution law. So here also, yeah, if you see the the presentation, that means the PDF, then you are able to know that this K is actually, or K equilibrium is your dissociation constant of the electrolyte, and here this alpha is your what, this alpha is your the degree of dissociation. Okay, so this is actually degree of dissociation, okay. And actually we can calculate the degree of dissociation by using this formula. Okay, so that means we can calculate the degree of dissociation of that molecules or that electrolytes by knowing the the molar conductance and the molar conductance at infinite dilutions. Okay, understand? So actually this can be calculated from what? This can be calculated from the kappa value, that means your specific conductance. So from a specific conductance, that means from conductance measurement we can calculate specific conductance. Okay, so from that specific conductance we can calculate molar conductance. Okay, so if we have that molar conductance value, then we can have that alpha value. So once we have that alpha value, we can calculate the your K equilibrium, that means dissociation constant of that electrolytes. So that means we can use conductance measurement to get our K equilibrium value. Okay, so it is very important and very interesting now. And this is actually this is actually the mathematical expressions of, or mathematical description of, or explanation of, you can say that mathematical explanations of Ostwald dilution law. So this is what, this is your Ostwald's dilution law. Okay, so this is your mathematical expressions. And always remember one point, that this the Arrhenius theory and this Ostwald law is only applicable for reversible reactions. Actually we have already discussed about this one, why we only we can apply the Arrhenius and this law for reversible reaction, because we cannot use it in case of strong electrolyte, because strong electrolyte will not going to show or exhibits the reversible reactions. So always remember this point. Okay, I hope you understand this to that means the Arrhenius theory and Ostwald law. So in the next the next topic we will going to discuss about some effects. Okay, some very important effects which are observed in electrochemistry. Okay.